So this is a standard result in stochastic thermodynamics that tells you if you have a slow process that the dissipated work will always be proportional to the fluctuations in work. And this thing is connected to what's known as thermodynamic geometry. So I'll give you a little overview of what this is. So basically this is a way of representing thermodynamic processes in a geometric way, and you can use this to find sort of optimal processes. So this dissipation relation and the geometry associated with it is it's all classical. So what we've worked on is doing the quantum generalization of this result. So I'll show you what happens when you go to the quantum regime to this dissipation relation. What we'll see is you get new modifications which stem from quantum uncertainty. This will be related to what's known as the Wigner-Yanase Skew information. So I'll talk about what these modifications are, what they mean physically for work extraction, how to witness them experimentally. And finally, I'll talk about how this also connects to thermodynamic geometry, but again in the quantum setting. So the main motivation for this work is to consider a very general question, which is, say we're constructing some engine of any size. Two important quantities we want to consider is the efficiency and reliability of whatever process we construct. So generally you want a process to be efficient so that you get as much work out as possible, allowed by the second law. But you would also want such a process to be reliable, so you'd want to minimize the amount of fluctuations you have in the work output. So this is just a sort of optimization problem. Now, if we know that if you take an infinitely slow process, you'll fulfill both of these things 100%. So if you take an engine, you drive it infinitely slow, then you'll get the dissipated work will be 0 and there'll be no fluctuations, but it's an infinite process, so we want to consider what can you do in finite time. So the regime I'll be talking about is slow processes that are finite but close to being efficient and reliable. So for the classical setup of this, say we have some small system that we're driving in time via some Hamiltonian, and is connected to some thermal bath. So the second law tells us that the dissipated work will always be positive. So the work will always be greater than its equilibrium for energy change. Now secondly, if the system is small, we're also going to get fluctuations in the work we get out. So this dissipation relation I'm talking about says that if the duration of the process is slow enough, then the dissipated work will be proportional to the fluctuations. So this was originally presented by Chris Jarzynski in his original paper on the Jarzynski quality. He didn't give a proper derivation of it. It comes as a consequence of the Jarzynski quality, but he sort of gave a phenomenological argument for why it should hold. But it wasn't until about 7 years later when it was properly proven. So it's proven by Seifert and Speck in this paper down here. So the way that they prove it is they treat the system as an open system here, described by some Fokker-Planck equation. So this is an equation for a small system weakly coupled to a bath with some time-dependent Hamiltonian. And the only assumption they take is that the instantaneous stationary state of this open system is always a Gibbs state. So you're driving your system in time, and the bath is tending to want to bring it to its instantaneous Gibbs state. So in classical thermodynamics, the work's a random variable, and you can compute it from looking at the integrating the power over some trajectory up to some time. So what Seifert and Speck showed is that if the process is slow enough, so if you take the time in which you do this to be a very large number, the distribution, so the statistics of this work variable, become Gaussian. So the shape of the work distribution becomes Gaussian to this order. So in the infinite time limit, this becomes a delta function eventually. So the fluctuations go to 0, and it becomes peaked on the free energy change. So this is what we expect. So what happens then is if you have a Gaussian work distribution, then you take the Jarzynski equality, which a lot of people are familiar with. So this relates the exponential work to the free energy change. If you plug this into here, you immediately get out this dissipation relation. So it's very neat. So they proved it with fairly minimal assumptions. So there's one fundamental consequence of this, which it implies that in the classical regime, the most efficient process is going to be the most reliable. So if you choose the optimal process which minimizes dissipation, you're automatically going to minimize fluctuations because they're proportional to each other. So if you want to construct optimal processes, this is where you turn to this thermodynamic geometry. So I think John mentioned in his talk already this paper by Crookes, this measuring thermodynamic length. So Crookes shows that for slow processes, the dissipated work is related to a metric tensor, which is this Fisher-Rao metric over the manifold of thermal states. So what you can do is you can use sort of differential geometry to find the geodesics through this space of thermal states, and this tells you what the best process would be in order to minimize your dissipation. So it tells you how to change these your Hamiltonian optimally. And you know that any geodesic that minimizes this will also minimize the fluctuations. So you can do both things at the same time. So going to the quantum scenario, the questions are, firstly, if we have a slowly driven quantum system, does it satisfy this dissipation relation? Which surprisingly no one's proven before. I don't know why, but second question is, what is the shape of this distribution in the quantum case? Is it Gaussian, just like in the classical case? And do we get the same thing where the most efficient process is also the one with minimal fluctuations? The answer to these will be no, all three of these. And then the final thing is, can we also generalize this notion of thermodynamic geometry to the quantum case? And what changes? So I'll discuss all of this now. So in the quantum setup, we again remember we're working in for slow processes, so the total time will always be really large. So we have some total Hamiltonian where we're only driving the system degrees of freedom, and we have a bath that's with some interaction that's very weak. So the way or at least the way we're defining work here is from the two projective measurement scheme. So what you do here is whatever your initial total state is, you measure the initial energy, evolve it unitarily, so this whole thing evolves unitarily due to this change in Hamiltonian, and then you do a final measurement. So this will give you some moment generating function, which tells you what the work moments will be. So this is just the standard way of treating work in fluctuating work. So similar to the way Seifert and Speck set up their classical problem, we assume that the reduced dynamics of the system is given by some Lindblad equation. And we also assume that if you fix the Hamiltonian at any given time, that the stationary state of this equation will be a instantaneous thermal state. So what you can do, there's this really nice paper here by Covino, Mario, and Giovanetti where they show that you can always expand the solution to this equation in powers of the duration. So the zero term will be the thermal state. So this is so if you have an infinite process, you effectively will always stay in equilibrium, and the dissipated work will be zero. But what they do in this paper is they figure out what the higher order corrections to this are. So our task here is then, for slow processes, we want to evaluate what the correction, use the correction to first order in tau, and check if this dissipation relation actually holds. So what we did was we looked at the fluctuations in work. So this is the variance in work. And just simply expanded it in powers of 1 over tau. So we drop the second order terms, and we get this expression here. So the different parts of this. So the P here is the power operator. So this is just the rate of change of the system Hamiltonian. remember pi of t is the thermal state. This S is a linear operator, which, when it acts on A, it gives you back this anti-commutator here. And finally, we have this L plus. So this is something known as the Drazen inverse of the Lindbladian. So remember, the Lindbladian has a 0 eigenvalue, so it's non-invertible, but you can define this kind of pseudo-inverse, which has a certain set of conditions which it must fulfill, but it's a uniquely defined operator. So I guess when you see this throughout here, just think of it as some kind of pseudo-inverse of the Lindbladian. So it contains information about how the system's relaxing. Right, so you can also do the same thing for the dissipated work. So this was actually done in a previous paper by Scandi and Perrin-Lebert. So they did exactly the same thing. So they just expanded the average dissipation in powers of 1 over tau. They get a very similar expression. So the only difference here is so if you remember for the fluctuations, we have this S linear operator here. So now they have a different linear operator coming into this, which is this J. Now the crucial point is these two things are only the same if power and the Hamiltonian commute. So what we find is that we get, when we put these two results together, we get a modified fluctuation dissipation relation. So you actually find out that the dissipated work is not proportional to the fluctuations. And it's all to do with the fact that the Hamiltonian will not generally commute with its power. So we get this extra term here. So this Q is the quantum correction, and it looks like this. So it's related to the fact that the thermal state will not commute with the power. So it only vanishes in the commuting case, and it's a positive quantity. So the result is that you actually get excess work fluctuations in the quantum case. So this Q turns out to be related to this Wigner-Yanase skew information. So this is a quantity it's a generalization of the variance. So it's a way of measuring the quantum uncertainty in observable for a mixed state. So it's a positive quantity that vanishes if rho and A commute, and it reduces the variance if rho is a pure state. And finally, it's also convex, so it can only decrease under classical mixing. So this was proposed by Wigner-Yanase in the 60s. So they suggested this quantity here as a candidate for some measure of quantum uncertainty. But as with all measures in quantum information, there's an infinite family of different ones you could choose. And there's a general recipe for constructing these measures. The one I want to focus on is this one here. So you're basically taking an inner product of these commutators. So it's quantifying the off-diagonal elements of the observable A in some way. And this is precisely what we have in our correction. So if you look at it here, it looks very similar. So the only difference here is it's got this Drazen inverse appearing inside here. So to see why this is the skew information, we'll take a simple example. So take very simple Lindbladian, so just a perfectly thermalizing one. So you figure out that the Drazen inverse is actually just the identity. So our correction term in this dissipation relation is just exactly this skew information that I just showed you. So the correction term is effectively measuring the quantum uncertainty in the power as you evolve your system. So for more general Lindbladians, it gets modified slightly. So this is a complicated expression, but the point is that when you have a general Lindbladian, you get this extra factor in front of the skew information, which just quantifies a sort of a time scale over which the off-diagonal terms sort of decay to equilibrium. So that our correction is still the skew information, it's just weighted by this extra time scale, which depends on the bath. So remember I said that in the classical case you get a Gaussian work distribution, so in the quantum case this no longer holds true. There's a neat way of proving this. So we we know that the Jarzynski equality will hold in the quantum case. So when we expand this in terms of the cumulants, we find that if the distribution was Gaussian, then we know that its higher order cumulants would all be 0. But these are actually equal to our quantum correction. So if you have these, if the power doesn't commute with energy, then you're going to get a non-Gaussian distribution. So we can actually prove that this is an if and only if case. So the only slowly driven quantum systems are Gaussian if and only if energy and power commute. So it means we have a way of actually witnessing these corrections, because you just need to access the work statistics, and it directly gives you a way of measuring this quantum correction term. So yeah, you can either, so there's various ways of actually measuring these. So you can either do a measurement on the whole Hilbert space, which is probably unfeasible, but there's alternative measurement schemes where you locally couple to system observables, and you can get these cumulants out. So we have a way of actually witnessing this correction thing. Right, so the final part of the talk, I'm going to talk about geometry and how this relates to this thermodynamic geometry. So what we can do is we can decompose our Hamiltonian into a set of parameters like this. And what you find is the fluctuations and dissipation are actually related to different metrics over the space of thermal states. So these are positive symmetric metric tensors here. So these actually both reduce to this Fisher-Rao metric in the commuting case. But we have this interesting situation where in the quantum case we actually have two different geometric structures here. So these are the formulas for them. But you can interpret both of these things as action, sort of an action functional over the space of these parameters. So if we want to find optimal processes, we just minimize the action of these metrics. I'll just skip over that, but I think I'm running out of time. Right, so if we want to find optimal paths, what we do is we take the Euler-Lagrange equations. But the key point is that if we find out the path of least action, which is equivalent to like the shortest path in this manifold, because we have two different metrics, the geodesics will not be the same. So in other words, the process of minimal dissipation is no longer the process of minimal fluctuations. So this is completely contrasts with the classical case. So you can't find a process which will be both efficient and reliable anymore. So the way to see this is we can actually take a convex combination of the fluctuations and the dissipation. So we take a convex combination of the metrics, we minimize the action, and we find that the optimal path will actually depend on this alpha parameter. So it's only in the classical case where this thing becomes independent. Yeah, so path of minimal fluctuations is not the same as the path of minimal dissipation, unless you have everything commuting. So I'll show you some examples. So yeah, take the simple driven harmonic oscillator. So we're driving the frequency in time. We want to know what's the optimal way to drive this frequency to minimize fluctuations, minimize dissipation. So the derivative of this power operator is not going to commute anymore. So this is a plot of these different metrics. So the green line here is this skew information, plotted as a function of inverse temperature. The blue line here is this is for the dissipation, and the orange line is for the fluctuations. So we see in the high temperature limit, the fluctuation metric and dissipation metric become the same thing. This is the classical scenario. So both of these become the Fisher information, and the skew information doesn't matter anymore because these diverge. And then in the low temperature limit, all of the fluctuations become equal to the skew information. So I can plot this correction term, so as a function of temperature. So we just take some process, say like a linear change in the frequency, and this area under the curve is showing us this correction here, the skew information, as a function of temperature. So as we go to, so this is inverse temperature, so as we go to the low temperature regime, we see this grow more and more. So we only recover this classical dissipation relation in the high temperature limit. Okay. So this is the optimal routes. I'll finish now. So this is showing that if you so the blue line here would be the path of minimal dissipation, the red line's the path of minimal fluctuations, and then you have intermediate processes. So this is just highlighting the fact that the optimal routes will not coincide anymore because of this. So I'll skip this. It's just showing the same thing essentially. Okay, so I'll summarize. So what have we shown? We've shown that for slowly driven quantum systems, this fluctuation dissipation relation breaks down, and this is because power and energy don't commute anymore. And we get an additional term that corrects it, which is related to this skew information. This leads to a non-Gaussian work distribution that we can witness. And finally, the path of minimal dissipation is not the one of minimal fluctuations. Instead, we have to find an optimal trade-off between the two. So this paper will appear on arXiv in a couple of weeks. So this is the title here. So it's joint work with Matteo Scandi, Janet Anders, and Marty Perenelle-Lebet. And I think I'll conclude there. So thanks for listening.
Questions?
Yeah, thanks for a very nice talk. Just clarification. So, I mean, you're